Hi guys, we're going to talk about how to separate mixtures in a minute using the characteristic properties. Previously, we only used characteristic properties to identify substances. Now we're going to turn it around and use them to separate substances. But before we do that, let's take a second and make sure we understand how matter is classified. On the quiz, I'll probably have you fill in parts of this chart for me. So really take a good look at it and make sure you follow and understand what's going on here. We break matter into two big categories. You're either a pure substance, sometimes just called a substance, or you're a mixture. Well, what's the difference? Well, pure substances come in two varieties. They are either elements or compounds, and an element is just made up of all the same type of atom. And you can find all the different atoms that are in the universe on a periodic table of the elements, and there's somewhere around 109 to 115 or so elements. And the reason I can't be exact is because there are some elements that have been created by human beings in the lab that don't really exist in nature, and some periodic tables put those on and some don't. But there's a lot of different atoms. Everything in the universe, all matter, is built from those atoms. They're sort of like the Legos or building blocks of the universe. So no matter what you have, it's made of atoms. The question is the substance you're looking at all one type of atom, or is there more than one type of atom? If there's more than one type of atom, the next question is, are the atoms bonded chemically to each other? If they are, you have what's called a compound, and compounds are also considered pure substances. Water's a really good example. Water contains two atoms, hydrogen and oxygen, and they're not just mixed together, they're actually chemically bonded to one another to form the compound water. So you get that oxygen atom with the two hydrogens actually attached chemically. And what that means is the hydrogen and the oxygen no longer behave like hydrogen and oxygen atoms. They behave like water molecules. Hydrogen as a gas in its elemental form is explosive, right? We take a little lit splint and put it underneath a test tube of hydrogen. It gives off that loud pop noise, right? Oxygen relights a flame that's going out. And water doesn't do either of those things. Not only is it not a gas, but it's also not flammable or combustible. So the properties are totally changed, and that's what tells us that the hydrogen and the oxygen aren't just mixed together, they're bonded to each other chemically. Hydrogen and oxygen are mixed together in the air, and the hydrogen that's in the air is just there's not enough of it for the air to be combustible. But there's enough oxygen in the air for air to support a flame. Okay, so what if you're not one of these two things? Well, then that means that you are a mixture. And that's what this tutorial is really about, is separating of mixtures or separation of mixtures. There are ways to separate compounds into their elements, and we will do some of that later, but this little mini unit is totally about separating mixtures. So there's two kinds of mixtures, homogeneous and heterogeneous. A homogeneous mixture is a solution. By definition, the only way to get a perfectly evenly mixed, totally uniform mixture where every particle is evenly distributed in the other particles, the only way to do that is if the atoms or molecules involved are attracted to each other, and when you put them in either a liquid or a gaseous state, they do their own mixing. They stir themselves up with those attractions. And that only happens in the process of dissolving. So the only way to get a homogeneous mixture is if the substances you're mixing together, one of them dissolves the other one. In the lab that you just completed where you had to identify your metals, some of you had alloys. Alloys are metals that are in mixture form, and they are homogeneous mixtures, and the way that you get a metal mixture is by melting down the two metals you want to mix together and then letting them sit, and they will mix themselves so that when they cool off, you have each atom of one metal evenly distributed in the atoms of the other metal, and that's how you get an alloy, which is a homogeneous mixture. It probably seems weird to think of metals as being in solution because you think of solutions as being liquids. It had to be melted down and turned to a liquid to create a solution of metal, but it then freezes as the temperature lowers. Here's an example of a heterogeneous mixture. Something like granite is not all the same throughout. Different parts of the rock have different colors and different textures, and that's because it's a very unevenly mixed, conglomeration of different rocks that have sort of been glued together over time. And that's what most mixtures are like. Most mixtures are heterogeneous. And that's mostly what you're going to work with in this class, but not always. Okay, so now that you've looked at this chart, what are the separation techniques that we're going to do? I'm going to just give you an overview here, and then in the next set of tutorials, you'll learn each technique with its own tutorial. Okay, so we're going to create a little chart here. And I'm going to go through 5 different separation techniques. And for each technique, I want you to think about what characteristic property am I using to make this technique work. The first separation technique that you want to use is, silly enough, it's called magnetism, which is really obvious. Let's say you have a mixture and it contains a magnetic metal, like iron. Well, the easiest way to get that magnetic metal out of the mixture would be to use the magnet, right? And pull that iron away from everything else. So that's kind of like the simplest separation technique we have. And the characteristic property that's being used is also called magnetism. Just wanted to get that one out of the way. Okay, another technique you could use is called filtration. We've used this a few times. When you filter something, what do? Well, let's take as an example a mixture of coffee grinds and water. How do you filter the coffee grinds away from the water? Well, you use some kind of filter, and in that case, it's a coffee filter, right, which is kind of made of paper or cloth, right, depending. And here's the key thing. The coffee that you get as a result doesn't contain the actual coffee grounds, right? But it does turn color. Why does it turn color? Well, because some of the material that's in those coffee grounds actually must be dissolving, right? If you think about it. And that dissolved material is what gives you nice brown looking coffee. Same thing with tea, right? So in this class, we filtered away our copper from our copper sulfate solution after our metals reacted with them. And so you use a funnel and a piece of filter paper and you get your solid in one place and your liquid in another. And anything that dissolves goes with your liquid. Because if something's dissolved, the particles are small enough that they'll fit through the filter just like your liquid particles. So what is the characteristic property that you need in order to do filtration? Believe it or not, it's solubility. Because the only way you can filter one substance away from another is if one substance dissolves and the other doesn't. And that characteristic property is called solubility. If one thing is soluble and another's not soluble, then you can use filtration. Here's a kind of a cool technique. It's called flotation. When you use flotation, you add your mixture to water or some other liquid, and some parts of it float and some parts sink, and then you can skim the floating stuff off the top. Now, why would some things float and other things sink? What characteristic property must they have being very different from each other in order for that to happen? Density. Things that are more dense than water will sink in water. Things that are less dense than water will float in water. So if you have two solids, both of which don't dissolve, and you put them both in water, the one that is less dense than the water will float to the top. All right, here's a technique that has a really long name. It's called fractional distillation. Let's see if I can fit it all in here. Fractional distillation. Holy shnikes, I think I did it. There you go. Fractional means part of a whole. If something's fractional, it's a part, right? It's part of a whole. Distill means to purify. Fractional distillation is a technique where you have a mixture of liquids, let's say water mixed with alcohol. And then what you do is you heat it and boil it. And as you boil it, the lower boiling alcohol boils away before the water does. And if you hook this up to a setup that's similar to a gas trap, kind of like we did with the baking soda, where you have that glass bend, right? You can actually turn one of your liquids to a gas, let it travel through that tube. Instead of it going through that tube to a gas trap, have it go into another test tube. And by the time that hot gas gets all the way away from your flame, it'll have cooled back off, turned back into a liquid, and recondense in your test tube. And when that happens, you're going to have the liquid that boiled away captured in a second test tube, and the liquid that hasn't boiled away yet left behind in the starting test tube. So this depends on your different liquids having different boiling points. Very useful technique. And then last but not least, we're going to do a technique called fractional crystallization. Fractional crystallization. Crystallization. Almost fit that one. Kind of had to fudge it at the end there. Fractional crystallization is similar to filtration, only this time both of your substances are going to dissolve. So they're both soluble, but one of them is more soluble than the other at a high temperature. This is a really tricky technique, but very useful, and I will show it to you. So the difference between simple filtration and fractional crystallization is that with regular filtration, you don't have to heat up your solvent. You don't have to heat up the liquid that you're dissolving in. But with fractional crystallization, you'll have to heat it up and filter, and then let it cool and filter again, because you're going to get different things at different temperatures. And it's a pretty interesting technique. For now, all you need to know are the two charts, the one on the previous slide and this one, to be ready to take your quiz. In class tomorrow, we will talk at length about each of these techniques, and I'll give you more tutorials, and then we'll start doing labs with them. And then the final project with this is actually going to be part of your final exam, where you will have to separate a very complex mixture, but you'll be able to do it by then, so don't worry. Okay, see you guys in class.